Hello, good evening, everybody. My name is Kristen Gonzalez-Vega, and you are joining us for AP Physics C, Electricity and Magnetism. I am in Frisco, Texas, where I teach AP Physics 1 and C at Reedy High School, and I am joined, like always, by my friend, Roger.
Hi there, everybody. Welcome. Thanks for joining us. I'm Roger Siegel, and coming to you live from Sarasota, Florida.
Okay, so like we said, this is AP Physics C, Electricity and Magnetism. If this is your first time joining us, welcome. And if not, welcome back. We have been talking about circuits the past couple days, and we are going to continue that today with going over power in addition to our current and resistance. So we're going to add in that power. Again, my name is Kristen, and Roger is joining us as well from Florida. And tonight we have the following for our objectives, what we're going to be able to do. So we are going to derive expressions to relate current, voltage, and resistance to the rate at which heat is produced in a resistor. We're going to calculate voltage, current, and power dissipation for any resistor in a circuit containing a network of known resistors. We're going to calculate relationships between potential difference, current, resistance, and power for any part of a circuit, given some characteristics of the circuit, such as the battery voltage, if you have a resistor in series or parallel. And then we're going to start talking about Kirchhoff's laws and rules and going over that loop and junction rule, which we'll do more of tomorrow and the following night. So let's talk about what power is. We talk about power a lot in mechanics, and that power is work over time or force times velocity, the rate at which work is being done. So it's the same thing here, but really we talk about it more about the rate at which energy is dissipated in our circuit. So we can look at the heat that is being converted from that electrical energy and kinetic energy of those charges. And we can look at that in terms of the resistance, the current, the voltage. There's lots of different equations we can use to talk about power. And it's measured in watts. The variable is capital P. Another symbol or units we could use instead of watts is that it's a joule per second, right? The rate at which energy is being used in the circuit or dissipated. The main equation that we use for power is that P equals I times V. That I is the current, V is that potential difference. But we can also substitute in using Ohm's law and get that P is I squared times R or V squared over R. And these, a lot of times, I think are more useful because when you change something in a circuit, a lot of times you're going to be asked questions about brightness of a bulb, right? So the brightness of a bulb relates to the power. The greater that power, the greater the wattage of your bulb, that more of that energy is being converted in that same amount of time. So you get a brighter bulb. But what we do when we put in another element into our circuit is we are changing that current and that voltage into each light bulb, right? So not from the battery, but for each element in the circuit, that's going to change. So your current's changing and your potential difference is changing. And sometimes that can get really confusing. But if we're looking at one bulb, the resistance of that one bulb won't change. So if we're adding or changing things in the circuit, sometimes it's easier to use one of those other two equations because you can easily see what's happening with the current or the potential difference in that part. And then that resistance wouldn't be changing, and you only have one changing variable instead of two. The other thing we're going to look at is we're going to look at our loop and our junction rule. So the loop rule, which goes back to conservation of energy, states that the potential difference that we gain in any loop of a circuit has to be equal to the potential differences that we lose, or the sum of those potential differences in our circuit in one loop. So what that means is, if we look here at our circuit, well, we've got our battery that has an EMF of 42 volts. We have the positive terminal here indicated by that longer side of the battery, and we have the negative terminal indicated by the shorter side of the battery. And we go by conventional current, which says that the charges are going to go from the positive terminal. So that current is going to flow out to the left here and around the circuit. But as we go around and we trace that current, It's going to go into our light bulb here, but then we get to this part right here, right? This is what we call the junction. That current can split off, and some of that current's going to go here. And so this around, it gets back here and goes back to the battery. This would be one loop. Okay, if I change the colors, well, what if instead we look at, as we go, we leave the battery, we go around, we go through this light bulb, some of that current's going to go down through this branch instead and go around and back. So that would be loop 2. So this circuit has 2 loops for it. So if we go around in that loop, our potential difference gains, which would be the battery. So if I write an equation using that loop rule, or right over here on that loop rule side, I would say, well, the gains, which is the EMF of the battery, that's a positive potential difference. Well, as we go through light bulb A, we're gonna have a potential difference drop across here. So I would say minus whatever that potential difference across A is. So as we keep going around this outer loop, we get to light bulb C. So again, that's another drop. So minus the potential difference across C. When I get back to here, by the time I get to the battery, I should have a potential difference now of 0, right? So our gains equal our drops. You could also write it as the EMF of the battery equals VA plus VB. Okay. We could do that for same thing then for the loop 1, or this top loop. That would be the EMF of the battery minus, again, we've got light bulb A in that loop, so the potential difference across A. And then as we go around, we've got bulb B. So minus the potential difference across B equals 0. And so this can be useful for a couple of different reasons. A, this gives us why that potential difference is the same in parallel. Because if I only had 2 light bulbs that were in parallel with each other, and let's say it's a 10-volt battery. Well, if we go around and we trace those loops, so if we go around this bottom loop, well, I'm gaining 10 volts and I only have 1 light bulb in that loop. Well, that means that this potential difference across this one also has to be 10 volts. Okay, well, if I do the top loop and go around, I'm gaining 10 volts from the battery. I'm losing, there's only 1 bulb in that loop, so it's 10 volts here too. Right, so it's not the same potential difference, but it's not like the exact same potential difference. But as we go around that loop, we end up having the same potential difference across this one as we do this one. So that's why our voltage is the same in parallel in a circuit. And we can use that to determine a lot of times what the potential difference is, or sometimes what the current is, but writing that loop rule can be really useful. The other rule that we have is the junction rule. And the junction rule, let's kind of back up a little bit here, states that the sum of the currents going into a junction has to equal the sum of all the currents going out. So maybe we have 1 current going in and we have 3 branches. The amount of that current going into that junction has to equal the total amount going out. So if we look at that here, I'm going to erase this stuff again. Let's look at that junction. Well, I've got a junction here and I've got a junction here. So we can look at either of those. Let's look at the one here on the left. So if I'm tracing my current around, I've got current going into that junction. Let's call that I1. But I have 2 currents coming out of that junction. I've got the current here and the current here. Let's call the current going into light bulb 2 I2, and let's call this one I3. Well, the ins have to equal the outs. So if I'm writing an equation for my junction rule, I would say, well, I1 going in, right, ins equal outs. Well, how many go in? Just 1. How many go out? 2. I2 plus I3 go out. So we're going to use these a lot more later. We'll touch on a couple of these today, but we're really going to practice more these loop and junction rules tomorrow and the next day. But always be thinking about those. And this is why in series currents are the same, because if you have no junctions, the current has to stay the same everywhere. Okay, so I'm going to stop here for a second, and Roger's going to take us through some practice with power.
Okay, Kristen, thanks a lot. So let's go ahead and do some of these problems. We're going to actually circle back to the one that you just saw in a few minutes, and we're going to do what's called a Verb Table, which is one of my favorites to do when I'm solving circuits. So let me go ahead and pop open the screen here, and let's get rid of that guy, and we'll say hello over here. Okay, great. All right, so let's look at this. First of all, okay, I am not getting any registration here. I'm going to pause for just 1 second. Kristen, this is going to take me about a half a second to finish, and then we'll go back. So stand by, everybody. Okay, excellent. Thank you. Okay, here we go. All right, so now let's take a look here. We've got a hairdryer, and it's rated at 1200 watts and 120 volts. Now, just so you know, anything that you plug directly in that's like a motor is probably going to be taking 1200 volts. Everything that we plug in our houses here in North America is 1200 volts. If we went to other places, it's 220, but that's what we use in our grid. And so 1200 watts, we want to know what's the resistance. Well, if you look on your formula sheet, you're going to see P is equal to IV, but with a little bit of manipulation, as we said with Ohm's law, we can say that that's equal to V squared over R, and it's also equal to I squared R. And remember, since this year's test is all open note, write out your formulas, write them all out. Okay, so let's go ahead and see. We're looking for we've got power and voltage, and we want resistance. So it looks like we're going to be doing this formula. P is equal to V squared over R. And so then we'll say that R is equal to V squared over P. And so our voltage, we said, is 120 volts. And we'll square that. And our power is 1200 watts. And so that gives us 1440 over 1200, 2 zeros cancel, 12 into 144 goes 12 times, or 12 ohms. So that's our resistance that caused that power. One thing, just a kind of rule of thumb is this: the more power that you're drawing in a circuit, the lower the resistance. Okay, so like your oven or an iron or your hot water heater, if that's electric, that's going to be a very low resistance because it's going to be drawing lots and lots of power. All right, let's keep going, and we'll do another one. So it says, now these are the kind of problems that we expect you might be asked to comment on, because this is the kind of what we call qualitative relationships that we hope that students who are proficient in AP Physics C are going to be able to do. And so let's practice this. Let's take a look. It says, which of the following graphs could represent the power dissipated as a function of resistance for a variable resistor connected to a constant voltage source? All right, so let's see what we're actually asked to relate here. We can relate to power, and we've got a variable resistor and a constant voltage. Well, here we go. We're back. We're going back to math class here. We want a function, power on the y-axis and resistance on the x-axis. So we're going to say that we want P as a function of R. And so power, we know, with voltage is V squared over R. So what we would say is P is 1 over R times V squared. Now look, they said V is constant. So P is proportional to 1 over R. That's our inverse relationship. So I'll bet you that's answer A. All right. All right, let's go on. Now, this is the one that Kristen was showing you some. We are going to attack this guy. We're going to go full out on this. It's going to take a few minutes, but I really want to take some time to dissect a circuit, pull it apart. And what I kind of like to tell my students is we're going to deconstruct it, and then we're going to reconstitute it. We're going to kind of go backwards and make it super simple. And then we're going to go back to the more complex, and we'll fill in all the details. All right, so the first thing, of course, we always want to read the problem. So it says light bulb A, B, and C are connected in the circuit shown above. List the bulbs in order of brightness from brightest to least bright. If any bulbs have the same brightness, state which ones. Justify your answer. All right, good. So let's really analyze this. Let's take a look at it. As I said, what we're going to do is we're going to come up with what's called a Verb Table. All right, V-I-R-P, and voltage, current, resistance, and power is a Verb Table. And I never taught this, but then I was grading the AP exams one year, and I saw a student drew it on their paper, and I thought, that's genius. I'm going to use that. So here we are. We're going to look at these different parts of the circuit. All right, so we have voltage, current, resistance, power, and they've been kind enough to label our resistors here. And so down here at the bottom, I usually, you got to kind of use your imagination with this one, but this is either the main branch, sometimes we'll talk about the main branch, or the effective resistance if we're talking about the resistance. All right, and we'll see if that makes sense. All right, so the first thing we're going to do is we're going to take this circuit, and we need to deconstruct it. We need to look at it and make it simpler because it's complex. If you look here, we've got always start at the positive end of the battery and then go for a walk. And so let's go for a walk, and we walk along this way, and we say, okay, well, we now have come to a light bulb, which is a resistor. And so we're going to go through that light bulb. There'll be a voltage drop because that's a resistor. And then we're going to come to a junction, which means that some of the current is, as Kristen was telling us, some of the current is going to go this way, and some of it is going to go this way. And the current that goes this way will go through this light bulb. There'll be a voltage drop. And the current that goes this way will go through this light bulb. There'll be a voltage drop. And then we come to another junction. And the current that was separated here on the left is now reunited. And if I could sing, I'd probably sing for you, but I can't. So they're reunited, and the current then returns to the battery. And the current that we have here leaving the battery must be the same as the current that comes back to the battery. So in order to simplify this, we're going to take these three resistors and break them down to one. So the first thing I'm going to do is I'm going to draw them as resistors, and I'm going to show, I hope you can see, I think you can, that these two resistors, right, these two batteries are actually in parallel. And how do I know they're in parallel? Well, because if you go from one to the other, you can go from one, you can easily go from one to the other like this without going through anything else. They're two sides. So let's go ahead and do that. And we will now say that we have here, this is 6 ohms, this is 12 ohms, and this is 10 ohms. Now, you would be fine to ask me, why did you draw it like this? Because it shows how they really look parallel. I like to draw them like that. So do you remember what we do with parallel circuits? We say 1 over R equals 1 over 6 plus 1 over 12, okay? And so with our calculators, that's 6 inverse plus 12 inverse. And then we take the inverse of that. I think this is faster with your calculator. So if you can get good at that as we practice, that's a really good thing to do. All right, so we add this together, and this comes out to be 4. So that means that these two together equal to 4 ohms. So now I'm going to redraw this over here. And now I have 10 ohms. And then I'm going to now redraw this branch as 1 4-ohm resistor. Now we know in reality, of course, it's not 1 4-ohm resistor. It's 2 resistors in parallel. But from the battery standpoint, that's all it feels. Now these two resistors are in series. And so that means my final picture, and you don't always have to draw this. I'm the teacher, I'm drawing all the things. If you're pressed for time, please don't draw them, that doesn't make any sense. If we add these together, that's 14 ohms. And so, and we were told earlier that this is 42 volts. So I'm going to go ahead and put some information in. We knew some of this before. In the main branch, we have 42 volts voltage gain, and we have 14 ohms of effective resistance. Now, what that allows me to do is to find the current in the main branch. And so I is equal to V, delta V over R. And so if I look in this main branch here, this circuit, I can see that there is a 42 volt gain right here. And that, so that delta V is 42, and my resistance is 14 ohms. And so that gives me 3 amps. So that means that I've got 3 amps going through this branch. So I'm going to go ahead and put 3 amps. And ladies and gentlemen, that's in the main branch. So I can put that here, 3 amps. I can put it here, 3 amps, and I'll put it here coming back in, 3 amps. All right, good. Now I'm going to leave the power until later, and then we'll come back and do that. Now let's look at, now we're going to move backwards. Just bear with me for a second. We spent a minute kind of going this way, right? Now we're going to go back the other way. We're going to start to fill in information in the reverse order. So now that we know that this is 3 amperes, we can find the voltage drop across this resistor. And how do I do that? Find that voltage drop. Remember, voltage is a drop from between 2 points. And I know that Ohm's law says delta V is equal to IR. So if I've got 3 amperes and 10 ohms, that's 3 amps times 10 ohms. That gives me 30 volts, a 30 voltage drop. All right, I'm going to put that in here. And that's my voltage drop across 10 ohms A. So I'm going to put 30 volts. Now, Krista was telling us about Kirchhoff's loop rule, always important. Let's look. In this loop, we're going to start here. We're going to have a 42 volt gain and then a 30 volt drop. Okay, so we go up by 42, we go down by 30. So if I gain 42 here, 42 volts, up, and then I drop 30 volts, well, what's left here before I come back? Well, what's left is 12 volts. So that means that I have 12 volts here. And C, notice that's across B. Okay, that's 12 volts across this. Notice these two are in parallel. And one thing I know about branches that are in parallel, they always have the same voltage drop across them. And so that means that C also has 12 volts drop across it. Now, we've gone backwards. Now we found the voltage drop. Now we can find the current. We know, we were given at the beginning, that this is 10 ohms. B is 12 ohms, and C is 6 ohms. And so now we can easily find the current. I is equal to delta V over R. And so that means we have a current. Well, we've already done this. That was 3 amperes. I just didn't write it in there. But now let's look at here. Let's look at what happens here. I want to talk about the junction because the junction rule is all important. Okay. Now here at the junction, we've got 3 amperes coming across here. So let's start with that. All right. So we've got 3 amperes coming out of our battery and going through this first light bulb. Now, here we come to a junction. Some of it has to go one way, some of it has to go another, okay? And so, and the total current going into the junction must equal the total current going out of the junction. That's Kirchhoff's junction rule. And so, well, we already found over here that the current we can find, or we haven't found, but we can find it really easily. The current I is V over R. Well, 12 volts divided by 12 ohms is 1 ampere. So let's go ahead and see that. That's B. And so over here, that means that there's 1 ampere. Now check this out. If I've got 3 amps coming in and 1 amp going this way, well, that means that this has to be the difference, or 2 amperes. And so I have 2 amperes going this way. Okay. And notice now There's 2 amperes arriving at this junction from the bottom here. There's 1 ampere arriving from the left. And so now, boom, they come together and they make 3 amperes. So that junction rule and the loop rule are what help us to figure out all this stuff. Now, we still haven't answered I didn't put this one in yet, so let me say we said that was 2 amperes. And so you can see also there's many ways that you can solve some of these problems. So don't be afraid to do it a different way if you see it that way. All right, now the last thing we want to do is it says, look, what is the brightness? And so the brightness is always going to be about power. So let's come over here and check that out. All right, so the brightness about power is equal to IV, or and 2 other formulas. So we've got 90 watts, okay, joules per second. Here we've got, that's 3 times 30 times 3. We've got 12 times 1, or 12 watts. Okay. We've got 12 times 2, or 24 watts. Okay, and if we look over here, we've got 42 times 3, or 126 watts. Okay, and so by the way, this is the only part of the table that is guaranteed to add up correctly. This will not add up to the bottom because these 2 are in parallel. You don't add them together. These won't add up because they're all parts of a whole, and these won't add up because we have reciprocal relationships. So that is another way. So now we can answer the question, which is the brightest. And the brightest one is the 10 ohm resistor, followed by the 12 ohm resistor. I'm sorry, followed by the 6 ohm light bulb. Then, so here are orders: 1, 2, and 3, or A, comma, C, comma, B. Boom, boom, boom. Okay. I got to tell you, it's important, ladies and gentlemen. Some of these problems are legacy problems, and it's not going to be long that we're going to be able to continue asking them, because there was a time when all light bulbs were incandescent light bulbs, and this problem really made sense. But if you read the fine print nowadays, you know that a 12-watt LED light bulb is just as bright as a 100-watt incandescent light bulb, and just as bright as a 20-watt fluorescent light bulb. So we're going to have to move away from this at some point. We got some legacy questions here that aren't going to make sense to the next generations of light bulb users, but we'll deal with that when we get to it. All right, last one, and then I'll send it back to Frisco. The last question, take a look at this. It says, in the diagram, lamps L1 and L2 are connected to a constant voltage power supply. If L1 burns out, the power delivered to L2 will be multiplied by a factor of 1. So let's go ahead and kind of analyze this. I do not jump into the math because it's not that hard. So let's look. We have these 2 lamps in parallel. And what does that mean? It means that each lamp is individually and independently hooked up to the voltage source. Now, when I say independently, you might say, well, how can that be? Because doesn't the current split here? And you would be right, the current does split, but the voltage doesn't. So if this is 100 volts, then the voltage drop across this lamp is 100 volts, and the voltage drop across this lamp is 100 volts. Now, if one of these burns out, guess what? It's now an open switch. So how much how much voltage do I have now that when this one burns out? Well, 100 volts. In other words, the voltage drop across the light bulb is constant. So since power, which gives us, which is what we're asked to find here, how much energy is dissipated, since power is V squared over R, and V doesn't change when I lose one of my light bulbs, that means that the power is the same, and it's multiplied by a factor of 1. So if one of them burns out, the other burns just as bright. And that's a tricky question. So, you know, it's easy to confound what would happen. I will also point out one thing, even though it wasn't asked, I have to answer it. The current does change in the circuit, okay? And I'll leave you to ponder that one. All right, Kristen, I think I've gotten got them going here. So why don't you take us home with some more awesome problems? We need your unmute.
There we go. Thanks. Why, you guys have to hear me? Oh. Okay, so let's look at this question right here. We have some different arrangements of resistors, and we want to know which one of these would dissipate 24 watts when connected to a 12-volt battery. They all have the same resistance. They're all 4 ohm resistors. So I want you to take a second to think this through, and we want to know which one of these combinations would dissipate 24 watts if we're connected to a battery. It is the same in each case, and 12 volts. Right, so we're only seeing part of it, but these are all connected to a battery. So we want to look at what we know, right? So we know what the power is. And we know what our potential difference of the EMF of our battery is. Okay, so what I always like to think of is if I know 2 things anywhere in my circuit, I can always find something else, right? We can either use Ohm's law or we can use that power equation, right? Or one of the other power equations, but let's just stick with PIV and VER, right? If we use Ohm's law, V equals IR, and we use power is I times V, well, if I know 2 things anywhere in my circuit, I can always find a third thing. So if we're looking at the battery and the EMF, and we want to know that we want the total power in the circuit to be 24 watts, and we have a kind of total voltage or a voltage potential difference of 12 volts. Well, if I know 2 things, I can find a third. So let's look at, would current help us here, or would resistance help us more? Well, if we have a group of resistors, probably not going to help me to find current. That's going to be an extra step. I want to know really dealing with the resistances here. So let's find resistance. Okay, so if I know, then let's use one of our other equations, that power is equal to V squared over R. And we know the power we want to be 24 watts. Our potential difference of our battery is 12 volts squared. Then we can solve for what equivalent resistance we want, or what we want our total resistance of the circuit to be. If we do 12 squared and divide it by our 24, we get that we want the total to be 6 ohms. Okay, so each of these is 4. So right away, if we want the equivalent resistance to be 6, well, I'm probably eliminating anything that's all straight series, right? Because if this is 4 and this is 4, well, this is going to give me 8 ohms. Right here, 4, 4, 4. Right, so we want to get rid of anything that's that. And if we are looking at just straight up parallel, we know that the more we add on, the less it's going to be, right? So I'm probably going to narrow it down to these, but really we could calculate it all out. But let's kind of have a look at these 2. If I want it to be 6 ohms, do I want more in series, do you think, or more in parallel? Because 6 is pretty close to 4. I'm trying to use all these reasoning techniques. If 6 is pretty close to 4, I'm probably going to want something that has more parallel and less series. So let's look at E just for time's sake here. If we look at E, and these are each 4 ohms, well, I have these 2 that are in parallel in this branch. So if we want to find that, we know that 1 over R in parallel is 1 over 4 plus 1 over 4. That gives me 2 over 4s, but that's again 1 over R. So if I flip that, I get that this is 2 ohms. So these have an equivalent resistance together. That's like 1 resistor that is 2 ohms. But they are in series with this 4 ohm resistor. So those we want to add. So if we added that 2 to that 4, then I'd get a total of 6 ohms. Whereas if we looked at C, and these are both 4 ohms, well, that would give me 8, and I would do 1 over 8 plus 1 over 4, right? It's not going to get us there. So E is the one that we want. Okay, I've got another problem here, which is actually a physics 1 problem, but I think it's good for the explaining, ranking, kind of reasoning through kinds of questions. So we have 3 circuits, 1, 2, and 3. The batteries are all identical and the light bulbs are all identical. So in circuit 1, we have a single light bulb is shown connected to the battery. In 2 and 3, we have 2 light bulbs. But as you can see in circuit 2, light bulbs B and C are connected in series, right? And circuit 3 is connected in parallel. If it's easier for you, it may be a good idea to kind of sketch out the schematic of this, right? Rather than looking at the picture, we could say, well, this is battery and 1 light bulb. This guy is battery and 2 light bulbs. And this one in parallel, 2 light bulbs. Okay. And we want to first rank the magnitudes of the potential differences across light bulbs A, B, C, D, and E from largest to smallest. If any of them have the same, then you can state that explicitly. And then briefly explain how you determined your ranking. So your ranking, I'm going to give you a minute. You tell me, rank the potential differences across these light bulbs and how you know. Okay, so these are where our loop rules and our junction rules are going to come into play. If we look at the schematics and change up my colors here, if the potential difference of the battery is the same in each case, well, if I compare circuit 1 and 2, well, circuit 1 has 1 potential difference gain and only 1 potential difference drop. So the potential difference across that 1 light bulb would be the same as the battery. So if it was a 1.5 volt battery, it would be a 1.5 volt potential difference across that light bulb. If we look at circuit 2, though, there are 2 light bulbs. So remember, our gains have to equal our drops. So if we had this same 1.5 volt battery, well, that potential difference has to be split between the 2, right? And if these light bulbs are identical, they have the same resistance, then it would be an equal. So this would be the EMF over 2, and this one would be the EMF over 2. Okay, and if we look at circuit 3, I got 2 loops. It's almost like we have 2 different one light bulb circuits. The potential difference in each one of these, though, is going to be the same as the battery because they're in parallel with the battery. So if we were to rank these then, what would be first? Well, all A, D, and E have the same potential difference. And then after that would be B and C, but those are equal since they are the same resistance. Okay, so how would we know that? If we're using our loop rules, then we know that A's potential difference drop is the same as D and E. Okay, what about if we look at these same batteries and they're all going to start with the same amount of usable energy? They're all connected to the light bulbs at the same time, and we want to know which of them will run out of that usable energy first and which one will run out of that usable energy last. So I'm going to give you another second to think about that. So we're going to connect up these light bulbs to the battery, turn them on, and which one of these batteries is going to run out of juice first and which one's going to run out of juice last, and how do you know? Okay, so what do we think? Which one is going to run out of juice first? How do we know which one's going to run out of that usable energy first? Well, the key word there is energy. And what can we relate that energy to? Power. It's what we've been talking about, right? So we want to use up the most energy in the shortest period of time. So we want a large amount of power. So how are we going to find which one of these draws the greatest amount of power from the battery? Okay, well, if we look at circuit 3 and circuit 1, well, we just said that they all have the same potential difference across them, right? Okay, but if we're looking here at the totals, right, we want to know just about the battery. If I want a good power, let's use I times V, right? So if they all have the same amount of potential difference, V, then which one of these is going to have the greatest amount of power? The one with the greatest amount of current being delivered from the battery. And how do we know it's going to have a big current? If we go to Ohm's law, we want a small amount of resistance. So which one of these circuits is going to have the smallest amount of resistance? If we want low resistance, how do we want our resistors? In series or in parallel? We want them in parallel, right? This guy, if this resistance is R, there's only one, then it would have a total resistance of R. If we compare this in series, how do we add them? We add them up. So this would be a total resistance of 2R. And circuit 3, if we did 1 over R and 1 over R, ends up being R over 2. Okay, so the greatest power is going to come from the lowest resistance, which is circuit 3. Okay, the other way we could think of it is that V squared over R, right? If all these batteries have the same potential difference, then we want the smallest amount of resistance to give us the biggest amount of power. So battery 3 is going to run out of juice first, followed by A, followed by B, C, right? Or battery into circuit 2, rather than naming those light bulbs. Okay. The last one I have here, which is kind of just driving it all home, is we have a beaker of water. So if we have this beaker of water, and I have it attached to a battery with an EMF of E, and I ask you if I add a resistor here in series to the circuit that's submerged in the water, right? So instead, if this was our beaker, right, and it's in the water. So this is what we call resistive heating, right? We can heat water with a heating element with that resistive heating. So if I add another resistor in series with this, how's that going to change the rate at which my water heats up? Is that going to heat my water quicker, slower? How would that change the rate at which it's heating the water versus if I added one in parallel? So instead, if we had our beaker with 2 of those resistors, oops, sorry, in parallel, a little bit distracted here, then how would that change the rate at which the water is heated? So I want to give you just a second with that. Okay, and then lastly, what is another way you could change the circuit without actually changing what the resistors in the circuit, right? Like not the number of resistors, right? Not adding or subtracting, but what else could you change in here that would heat the water faster? Okay, so let's look at it. What's adding a resistor in series going to do to the rate at which this water is being heated? So really we want to know what it's going to do to the power. We've been doing this all evening. If I add another resistor in here, then what's that going to do to the power? Well, if we've got the same potential difference or EMF being supplied by the battery, let's look at what that does. If I add another resistor in series, what does that do to our total resistance? It's going to increase it. And if I increase that resistance, what does it do to my power? It's going to decrease it. So I'm going to decrease the power, which is going to actually make it take longer for me to heat up my water. Okay, I need more time to get the same amount of energy than I had before. Okay, what about if I add a resistor in parallel? What's that going to do? Well, adding a resistor in parallel is going to decrease my total resistance. So that's going to increase my power. right? So I'm getting more bang for my buck. I'm getting more energy in that same amount of time. Right? What else could we do then to my circuit in order to make it heat up faster? So what could we do to that one individual resistor that is going to increase the power? Well, how did we get the resistance of one resistor? Right? We said that the resistance is equal to rho naught times L over A. So if I want to do what to the resistance to get more power? I want to decrease the resistance. So there's actually a few different things we could do here. We could change the material that my resistor is made up of. What do I want to do to the resistivity if I want a lower amount of resistance? Well, I want to lower that resistivity, right? I could change that shape or length of the resistor, right? The main idea here is that you want to decrease the resistance. The only thing this makes me think of that I want to add on to the end here that we haven't necessarily talked about is the difference between an ohmic and a non-ohmic resistor. And we don't really see it that often, but I think this is a good time to bring it up because if we look at an ohmic resistor obeys Ohm's law, just like it sounds. So if I were to actually make a graph, if I had a circuit with a resistor in it, and if I changed the potential difference, I have a variable power supply. If I change that voltage and I measured the current going through my resistor and I were to graph it, the potential difference versus the current, I would get a nice straight line, right? That resistance is constant no matter what potential difference or current is traveling through it. The slope of that, right, is the resistance. But there are some things like a light bulb that typically are non-ohmic, where if you have that incandescent light bulb on, it gets hotter and hotter. And that changes that resistance. So a non-ohmic would not be a nice linear graph. That would change as you increase that potential difference across it. You would not get a nice straight line. So I just wanted to touch on that really quick to kind of draw it all together at the end. So what we did, tonight is we talked about power, how you could find the rate at which that energy is dissipated in your circuit. We calculated some of that. We used a little bit of those loop and junction rules that we're gonna practice some more again tomorrow. So come back tomorrow, we're gonna do lots more with circuits. We're gonna look at what happens when you have a bunch of resistors. How can you find, again, kind of like Roger started, that current and that potential difference across any part of our circuit, and what happens as you change things in the circuit. So from Frisco, good night, and over to you, Roger.
Yeah, from Sarasota, thanks so much for tuning in. Thanks for working so hard at this really hard stuff, because it's going to pay off. You're going to pass and get the credit if you put the time in. All right. So thanks, Kristen. What do we'll see you tomorrow?
Yes, I'll be here.